Hello everybody, and welcome to exercise 4 on page 82 of the workbook here. Okay, let's read this example together. So consider the vector space V, and they give us a description of it here. So the set of all A, B, C, D, and R4 that satisfy this particular equation. Okay, first we'd like to explain why M equals the set that just contains one vector, 1, 3, 5, and 0, is a linearly independent subset of V. Okay, why don't we just go ahead and do that. That kind of gets the ball rolling here. So notice that first sentence is really asking us to do two things. Number one, to convince ourselves that it's linearly independent, and then number two, that it's a subset of V. We'll kind of take those one at a time. Okay, so the first part is a matter of kind of just remembering stuff that we did earlier in the course. We know that a set that has just one non-zero vector is going to be linearly independent. So I'm just going to say this for that. M is linearly independent because it contains one non-zero vector. Okay, I put that in the category of previous work that we've done. We already know that. Okay, so what about the other part of what they're asking us to show? They want us to convince ourselves that this is a subset of V. Okay, so what would it take to convince ourselves that this vector, 1, 3, 5, and 0, is really in V? Well, to be in V, that vector has to satisfy this equation. Okay, so all we really need to check is to see if that's a true statement with this particular vector that we're talking about. All right, so we claim that M is a subset of V because, okay, what we're going to do is to take the 1, 3, 5, and 0 as A, B, C, and D and just see what happens. So if we plug, I'm looking back up again at this equation that I'm underlining in green up here. Okay, so we'll take the A of 1, the B of 3, the C of 5, and the D of 0. Okay, those are just the A, B, C, and the D, okay, in the one vector that we have. And what we're hoping is that that equals 0. Let's see. So 1 minus 2 times 3, that's 1 minus 6 plus 5. Notice that sure enough, that equals 0. And so we have just confirmed that this equation that I'm underlining now in red really is a true statement. Okay, and that's all we need to do to confirm that M is a subset of V. Okay, so we've cleared the first hurdle here. Let's clear a little bit of clutter away. And now we're looking at the second sentence. Okay, then extend the set M to a basis for V. Okay, in other words, find a basis for V that contains M. Now this is a type of problem that we did way back in chapter 1, I think. It's been a while since we did this. Okay, so there's kind of a standard process for doing this. Okay, what we can do is to first find a generating set for V, okay, and then to kind of use matrix operations to figure out how do we now get a basis that contains the set M that we want. All right, so let's first see if we can find a generating set for V. Okay, and it helps to just redescribe V a little bit. Okay, so kind of going back up to the top of the page here, I'm going to underline that formula again in red. Notice that we can rewrite that by solving it for A. So we kind of rearrange that equation. A is equal to 2B minus C plus 3D. And that means we can rewrite V like this. Okay, the first coordinate is going to look like 2B minus C plus 3D. Okay, and then B, C, and D are going to stay the same. Okay, so B, C, and D can really be anything, but to guarantee that that 4 tuple is in V, we know that A has to equal, okay, that equation that we came up with at the top. All right, And so now we're going to rewrite that in the way that we've done quite often in the course. We can sort of pull that apart according to the variables. So starting with b, you can write that as b times 2, 1, 0, 0, just kind of looking at where the b's are in the various positions of our tuple, plus c times negative 1, 0, 1, 0, okay, plus d times 3, 0, 0, 1. Okay, and by doing that, we recognize that v is the span of three vectors. So 2, 1, 0, 0, negative 1, 0, 1, 0, and 3, 0, 0, 1. Okay, I'm going to just double check and make sure that I wrote everything right here. Okay, looks good. And so we can see our generating set now. We've written v as a linear combination of three vectors, and so G equals the set that contains those three vectors is a generating set for v. Is a generating set for v. Okay, let's give ourselves a little bit more space here. Okay, now we come to the key fact here. I think I might have said this out loud already, but I will re-emphasize it. Okay, we can add vectors to M. Remember, M was that set that just contained one vector that was given to us in the problem. We can do that to obtain a basis. And we had a process for doing that. Okay, the process looked like this. We kind of started from a matrix, and we'll start with the vector that we were given in M. That was 1, 3, 5, 0. And then what we're going to do is to append the three vectors in our generating set. Okay, so we'll write those down one by one. Negative 1, 0, 1, 0. Or whoops, sorry, I want to go in order here. Back up. So 2, 1, 0, 0, negative 1, 0, 1, 0, and 3, 0, 0, 1. Okay, and notice, just to kind of mark this, those last three vectors are the vectors that are in G. Okay, now before we do row operations on this, let's kind of just take stock of where we're going and why we're doing this. Okay, so the vectors in G, what we underlined in green, we already know that those are generating set for V. And 1, 3, 5, 0, that's also in V. So at the moment, these four vectors are too much. We don't need all of those vectors to get a basis. And so by doing row operations, what it's going to do is it's going to select for us, by picking out the pivot columns, exactly the vectors that we need to get a basis. So it's going to reduce this set of four vectors down to the right size to give us a basis. All right, so if we do that, kind of do the row operations here, and I'm using a calculator to do this, here's what the reduced matrix looks like. Okay, 2, negative 5, 0, 0, negative 1, 3, 0, 0, and 3, negative 9, 1, 0. All right, and we go ahead and circle our pivot positions, 1, negative 5, and 1. Notice that this picked out three columns for us, the first, the second, and the fourth. And so what we need to select to get our basis are the first, second, and the fourth columns of our original matrix. Okay, and so we're ready to state our answer here. So a basis for V that contains M is beta equals, and we'll just write down those three columns. Okay, so 1, 3, 5, 0, 2, 1, 0, 0, and 3, 0, 0, 1. Okay, and there's our answer. So kind of what made this work is the fact that we took the vector that was in M and deliberately made it our first column. That sort of forced this algorithm to choose that first column. Okay, and then the algorithm kind of told us which of the rest of the columns we need to add to have enough for a basis.